In Part 5 of the Unit 6 notes, we will be covering the names and formulas for polyatomic ions. A polyatomic ion is an ion which contains more than one element. Within the polyatomic ion, atoms are covalently bonded together, meaning that electrons are shared between the atoms. But the resulting structure still needs to gain or lose an electron in order to become more stable. It will then form an ionic bond with a metal, nonmetal, or another polyatomic ion. In the example below shows the process of an ammonium ion, NH4 plus 1, donating an electron it does not need to a nearby chlorine atom. The resulting ammonium chloride compound is more stable since both ions are now following the octet rule. So here we have nitrogen, which starts with 5 electrons shown in blue. 4 of them are going into the bonds for the hydrogen, so it would now have a stable octet with just those. This extra electron is no longer needed, so it can now be transferred over to a chlorine atom. That results in the positive and negative charges, which we would typically associate with an ionic bond. There are many polyatomic ions, but you are not expected to memorize them for this course. A PDF version of the list below will be given to you for reference. So here we can see our name for the ion on the left side, and then our ion with the charge on the right. When naming an ionic compound which contains a polyatomic anion, you do not change the ending like you would for a binary ionic compound. For example, CaNO3 would be called calcium nitrate, not calcium nitride. When writing the formula for a compound with a polyatomic ion, cross the charges as you normally would. If there are more than one of the polyatomic ion after crossing the charges, you must put the ion in parentheses. You should never replace the subscript of the polyatomic ion. For example, when writing a formula for calcium nitrate, you would cross the charges for Ca plus 2 and NO3 minus 1. The 3 in the NO3 would not be replaced. That's part of what nitrate is. It has 3 oxygens within the structure. Instead, you would put the nitrate within a set of parentheses and then show that you have 2 of the NO3s. There are 3 ways that polyatomic ions can form ionic compounds. You can have a positive metal, like sodium, and it can bond to a negative polyatomic ion. Here we have OH, which is hydroxide. You can also have a negative nonmetal, which is bonding to a positive polyatomic ion. Here we have a positive polyatomic ion in ammonium, and our negative nonmetal ion is chlorine. You can also have an instance of 2 polyatomic ions bonding together. Here we have the ammonium bonding to the hydroxide. What's interesting about this example is that we have ionic bonds occurring even though there are no metals present. So while most ionic compounds are going to be between a metal and a nonmetal, this isn't always the case. Another interesting fact is that you can have both ionic and covalent bonding within a compound when you have polyatomics. So here with the hydroxide part of this compound, O bonding to H, electrons are going to be shared between these 2 atoms. They are both nonmetals with similar desires for electrons. But when you are bonding sodium to the oxygen, metal to nonmetal, that is going to be an ionic bond, where electron transfer would occur. In this series of checkpoint questions, we are going to be writing out the name for the formulas. We're going to be starting off with AuOH3. The Au is gold. Remember that we need to look at the periodic table to determine if gold has more than one charge. It does. And since it does, I need to include the charge inside of the parentheses. The OH is a polyatomic ion. I can look that up on the polyatomic ion chart that I showed on a few slides prior. OH is hydroxide. Now, in order to determine the charge of the gold, I can cross the subscripts back up. It's important that you're crossing up the number of the polyatomic ion and not a number that is associated with what the polyatomic ion is. For example, here in hydroxide, there is 1 oxygen and 1 hydrogen. I'm not crossing that up. But the fact that there are 3 of the entire ion, that would cross back up. So it looks like gold would be a +3 and hydroxide would be a -1. This fits with what you would see on that chart. Hydroxide is a -1 charge. So this shows that this was never reduced. And this would be gold 3 hydroxide. Next up we have CaSO4. Ca is calcium. Calcium is a metal which is always the same charge, a +2. So I don't need to show that here. SO4 is the polyatomic ion sulfate. When you are looking up the ions, you need to be very careful because some of the names are very similar to each other. SO4 is sulfate, but if you had SO3, that would be sulfite with an ITE ending. In our next example, we have Sb, which is antimony. Antimony has more than one charge, so I'm going to include a parenthesis here. NO2 is the polyatomic ion nitrite. This is going to be similar to what we did in the first example. The 5 can cross back up, which means that antimony was likely a +5. There's 1 antimony, so nitrite is likely a -1, and we need to check to make sure that makes sense. If we look up nitrite on the list, it is a -1, so this was never reduced. That makes the charge 5. In our next example, we have Cs, which is cesium. Cesium is always the same charge, so no parentheses needed for this one. Cn is cyanide. In our next example, we have Al, which is aluminum. Aluminum is another metal which is always the same charge, so no parentheses this time. PO4 is phosphate, a polyatomic ion. Moving over to the right column, we have Na and ClO4. ClO4 is a polyatomic ion. Na is going to be sodium. Only 1 charge for sodium, so no parentheses. The ClO4 is perchlorate. This one is a little tricky, so I'm going to star it. Ca is calcium. And calcium is only ever 1 charge, so no parentheses needed. But there are 2 polyatomic ions with the formula of MnO4. The difference is the charge. One of the polyatomic ions has a -1 charge, and the other has a -2. Calcium is always a +2 charge, and it looks like there's 1 calcium for every 1 of this ion, MnO4. That means that this is likely going to be a -2 charge in order to cancel it, and that helps me to identify my polyatomic ion this time. This is going to be calcium manganate. The MnO4 with a -1 charge would be permanganate. In our next example, we have K, which is potassium. Potassium has 1 charge, and NO3 is nitrate. Here we have Li, which is lithium, and again, lithium is always the same charge, so no parentheses. CO3 is carbonate. Our next one is also a little tricky. We have Fe, which is iron. Iron has more than 1 charge, so I need a parentheses. SO3 is the polyatomic ion sulfite. Now, in order to determine the charge here, you might want to cross that 3 back up. But that 3 is part of what sulfite is. Instead, what you will want to cross up is how many sulfites there are. There's no parentheses, so that implies there's only 1 of them. So this is going to look like a +1 charge, but only if sulfite's a -1, because there's 1 iron. Now we have to take this a step further. Sulfite is never a -1 charge. It's always a -2. That means that this must have been reduced at some point. And if I have to double this charge in order to get it to where it's supposed to be, that means I have to double the other side too. So instead of being +1 -1, it's actually +2 -2, meaning that this is iron 2 sulfite. For this series of checkpoint questions, we are now going to be going in the opposite direction. So we are now going to be given the names and we are trying to write out the formulas. That means we're going to be crossing charges and reducing subscripts when possible. In our first example, we have magnesium, which has a +2 charge, and sulfite. Sulfite is a polyatomic ion, it's SO3, with a -2 charge. These charges are going to crisscross down, but because it's a 2 to 2 relationship, they are going to cancel out as well. So in the end, I'm just going to have one of each. My final formula would be MgSO3. In our next example, we have calcium with a +2 charge, and sulfate, which is SO4 with a -2. Notice the difference between sulfite and sulfate. That means a different number of oxygens within the formula. After these two cross down, the same thing is going to happen. They're going to cancel out. So I'm left with CaSO4. In our next example, we have hydronium. This is a positive polyatomic ion. It's H3O with a +1 charge. Fluoride refers to fluorine with a -1. The two ones cross down, and ones do not need to be written in the formula. So I have H3OF. Next up, we have platinum for cyanide. This time, the charge of the platinum is given because platinum has more than one potential charge, so we're being told which one to use. Cyanide is a polyatomic ion made of carbon and nitrogen. Together, they have a -1 charge. When these two values crisscross down, I am now going to have 1 platinum and 4 of my cyanides. Now, this part is incredibly important. You can't just put the 4 down at the end, because this 4 would only be attached to the nitrogen. I need to show that I have 4 of the entire polyatomic ion. This is the reason why we need the parentheses around that ion. So this would be PT parentheses Cn close parentheses and a 4 as a subscript. Next up, we have vanadium with a +5 charge and nitrite, which is NO2 with a -1. We're crisscrossing again, and we're going to end up with 5 of the nitrite and 1 of the vanadium. Just like before, our polyatomic ion has to go into a parentheses because there's more than one of it. My 5 is going to go on the outside. I am never replacing the subscript within the formula for the polyatomic. In our next example, we have sodium phosphate. Sodium has a +1 charge. Phosphate, which is PO4, has a -3 charge. When these two values crisscross down, I'm going to have 3 of the sodiums, so Na3. I only have 1 of the phosphates. That means that I don't need a parentheses this time. I only need a parentheses around the polyatomic if there's more than 1 of it. Next up, we have cobalt-3 hydroxide. Our cobalt is going to have a +3 charge. Hydroxide always has a -1. Crisscross down, and it looks like we're going to have 3 of the hydroxide. So CO, parentheses OH, and the 3 is going to go on the outside to show that we have 3 of the entire ion. Next up, we have ammonium phosphate. Ammonium is NH4 with a +1 charge. Phosphate is PO4 with a -3. These are going to crisscross down, and I'm going to have 3 of the ammonium. That means that I have NH4 in parentheses with a 3. That should be a 4 here with a 3 outside. And then we are going to have PO4, no parentheses needed for that part. So again, I apologize that it's a little messy here. It should be NH4 inside of parentheses with a 3 outside, and then PO4 with no parentheses needed. In our next example, we have potassium, which is a +1, and dichromate. Dichromate is Cr2O7, and this has a -2 charge. Those charges are going to crisscross down. We're going to have 2 of the potassiums now, and 1 of the dichromate. so Cr2O7. In our final example, we have titanium, which has a +4 charge. Titanium has more than one charge, so we're given that charge in the parentheses. Acetate is C2H3O2. This is a polyatomic ion which has 3 atoms inside of it, or 3 types of atoms. This has a -1 charge. I'm going to crisscross down. So I'm going to have one of the titaniums. The C2H3O2 is all going to be in parentheses, and there's going to be 4 of that. That concludes part 5 of the Unit 6 notes. When we come back in part 6, we will be looking at the structure of covalent compounds.